Last time we talked about black body radiation and photon statistics. That's the easy part of Bose-Einstein statistics. Regular Bose-Einstein statistics, in other words, using ordinary bosons other than photons, is a little bit more challenging. It's more challenging because you have a term in the expression that is attributable to the chemical potential. Chemical potential for photons is 0 because you can have as many of them as you want. But for ordinary bosons, that's not allowed. You have a limit. So that's going to make things a little more challenging. And we're going to have to determine chemical potential as a function of temperature. But in the final result, we're going to get a surprise. The surprise is going to be that if I have a gas of bosons at a low enough temperature, the gas will abruptly condense into the ground state as the temperature decreases. And all kinds of interesting properties will emerge from that. Bose-Einstein condensation, as it's called, was first predicted by Einstein in 1925. It was for sure produced in the lab in about 1995. In between that time, there have been some really interesting discussions, maybe arguments about whether liquid helium is indeed an example of a Bose-Einstein condensate at low enough temperatures. In some ways, it behaves like one. But I think in the final analysis, when we finish this unit, you probably will agree that maybe it's not really a Bose-Einstein condensate, but maybe it's the liquid equivalent. So, without any further ado, we're interested in for two reasons. One, Bose-Einstein condensation provides a phase transition that we can solve exactly mathematically. So that's kind of nice. But secondly, because liquid helium is rather familiar, it does exhibit features that are very, very similar to a Bose condensate. Let's talk about how this problem arises. Bose-Einstein condensation is predicted by, first of all, let's look at a density of states in momentum space. So in phase space, the number of states in a region, I can write as d3p, d3r, divided by 2 pi h bar cubed. So this is the number of states I would expect in a region of phase space. If I'm dealing with an ideal gas, nothing depends upon r. Therefore, if I integrate over d3r, all I'm going to get from that integral is going to be a volume. That makes life simple. I can write d3p as an integral in momentum space, 4 pi p squared dp. So the number of states between p and d and p plus dp then could just be written as the volume times 4 pi p squared dp divided by 2 pi h bar cubed. Having said that, as we all know, energy is a lot easier to work with than momentum is. And we know we can write our energy in terms of momentum as p squared over 2m. So what I want to do is move into a density of states where we're talking about the density with respect to energy. I can write dE as dE is a function of momentum, dP times dP. So the number of states per unit energy range I'll call it rho of E. I know I've used G before, but I'm using G for something else today. So we're going to use rho of E for this number of states per unit energy, rho of E dE. I'm going to write as 4 pi V over 2 pi h bar all cubed, p cubed dp dE dE. And since p squared over 2m is equal to energy, I can make this expression purely in terms of energy in the following way. Rho of E dE can be written as 4 pi V over 2 pi h bar cubed, everybody. Fix that. I'll write that as 4 pi square root of 2 V m to the 3 halves 2 pi h bar cubed e to the 1/2 dE. Now, we're dealing with bosons, so we have to incorporate spin into the mix as well. So I'm going to use the expression G is equal to 2s plus 1. I need a factor of G to multiply this number to account for the fact that I have spin states as well. But that's going to be simple because for bosons, let's assume we have a spin of 0. Therefore, the value for G is just going to be 1 anyway. So we can throw a G in there, but it's just going to be equal to 1. So your occupation number then, how many you're going to have, will look like this. I can write it as sum over Q, 1 over E to the E sub Q minus mu over KT minus 1. Bose-Einstein distribution. This is to say I can write this as rho of E times my Bose distribution. What that means is N is equal to 4 pi times V. G is 1, I'll leave it out. 2 square root of 2 m to the 3 halves divided by 2 pi h bar quantity cubed. Integral from 0 to infinity e to the 1/2 dE divided by e to the e minus mu over KT minus 1. Now, for bosons, mu is always negative. So, let's say we have a container of fixed volume V, and we hold it at some temperature T by a heat reservoir. If I want to keep putting particles into that container, I can do that, but mu, my chemical potential, has to adjust in order to keep this equation balanced. So if mu is negative, I keep adding particles, mu gets closer and closer and closer to a positive number. It approaches 0, in other words. So what that's telling me is that at some finite n, some finite number of particles, mu is going to be pushed almost to 0. That means I can't get any more particles in there. If I'm not allowed, if I can't change the chemical potential, it will not be favorable for me to add any more particles. So I'm kind of stuck. let's see if this actually happens. In other words, let's do this integral. We're going to set this integral up. But we're going to set it up assuming that mu is 0. And I'm going to make a variable substitution, which allows me to say that E minus mu over kt, or mu is 0, E over kt is equal to, I'm going to define that as x. So my integral looks like this. If I tabulate this integral, it will have a value of 2.31, which is equal to square root of pi over 2 times 2.612, if you're interested in where that comes from. What that means is that critical density, mass over volume at critical density, will be equal to 2.612 over some capital lambda cubed, where we define lambda as 2 pi h bar divided by square root 2 pi m kt. Okay, just to make the equations look a little bit simpler. So this is what will happen at critical density. On the other hand, suppose we reduce the critical temperature. So we take the temperature, drop it to the critical temperature. My critical temperature is going to be equal to 1 over 2.31 mK n over v to the 2/3 times 2 pi h bar squared divided by 4 pi square root of 2 to the 2/3. This is a sticky problem because at this point, particles will not be in localized states. They're going to overlap quantum mechanically. And this is going to be a problem. Okay, so here's where we stand. We recognize that the more particles we added, the closer the chemical potential became to approaching 0. So the question is, what happened to those particles? That's a really hard problem. But amazingly enough, we can look at a much easier problem, and it will give us a clue as to how to get through the rest of the way. Completely different physical situation. But it will give us a great clue. Let's take nitrogen gas. And let's start feeding nitrogen gas molecules into a fixed volume. Now let's do it at constant temperature. Let's make it 60 kelvins, okay? Because that's the temperature that's just above the triple point of nitrogen. I'm going to treat nitrogen like an ideal gas so that the number of molecules I have is going to be equal to PV over KT, ideal gas law. And we're going to count N and simultaneously measure the pressure as we add molecules to this container. And we're going to get a plot that looks something like this. So if I plot pressure versus the number of molecules I add, or particles, I get a plot that's linear first. And that slope, of course, is V over KT. But then, all of a sudden, at some number, the pressure doesn't change anymore. Fascinating. This is what happens. At some point, the ideal gas equation breaks down and the pressure stops changing. At this point, physically, liquid droplets begin to form in the container, and as I try to add more molecules, the liquid droplets grow, but the pressure doesn't change. So you're starting to get more liquid and less gas. This, of course, is what we call a first order phase change. It's condensation of vapor, and of course, we've reached a vapor pressure. This value is what we call the vapor pressure of nitrogen. What's this got to do with what we're doing? Let's go back to the Bose gas. But now what we want to do is to say, suppose we make a plot similar to the nitrogen plot. But on the y-axis, instead of plotting pressure, I'll plot n down here. But instead of plotting pressure, I'm going to plot y. Y is equal to the integral from 0 to infinity, e to the 1/2 dE divided by e to the e minus mu over kt minus 1. Well, the initial slope of this graph, if I plot y versus n, the initial slope is going to be equal to 4 pi, slope is equal to 4 pi square root of 2, m to the 2/3, 2 pi h bar cubed. That's going to be the slope. But again, at some critical value of n, y stops changing. So using this figure to describe a Bose gas, the break in this curve is going to happen at exactly when mu is 0. The chemical potential is 0. Now our equation can't keep track of the particles anymore. Okay, so we say something's broken. What did we do to cause this problem? Let's look back at any approximations that we made to get into this situation. First one we'll look at is, suppose we say, I wanted to write the sum as an integral, and in order to do that, kt had to be much, much greater than h bar squared over 2m times 2 pi over L cubed. Is that true? Well, actually it is. Because at t equal t critical, that's equivalent to saying n to the 2/3 must be much, much greater than 2.31 times 4 pi square root of 2 to the 3/2 over 2. Well, this number is on the order of 1. And n is on the order of 10 to the 23rd. So, of course that's true. That's not the problem. Okay, let's look at another mistake we might have made. Our density of states is going to be where the problem lies. Notice, we said our density of states was proportional to e to the 1/2. That implies that it should be 0 when energy is 0. Well, that's nonsense. Because when the energy is 0, or at the lowest possible state, rho should be 1, because all of these particles should be in the ground state. It's a boson. They can all be in the lowest energy state. So in other words, everything we did ignored all of the particles in the ground state. and it only was looking at particles in excited states. So, now this wouldn't be a problem for Fermi gases because you can have only one particle per energy level, and so you won't have many particles. You'll only have one particle in the ground state. Bosons are a completely different game. So for a Bose gas, the number of particles, the mean number of particles in the ground state, I can write as e to the minus mu over kt minus 1. And so the limit as mu goes to 0, look what happens. This goes to minus kt over mu. So the missing particles are disappearing into the ground state. And those particles that move into the ground state are what we call the Bose condensate. This is Bose condensation when that happens. So what we did is essentially to say that previous integral is only for particles that aren't in the ground state. Let's call that number, instead of that, let's call it n star. And that I can write as 0 to infinity rho of e dE over e to the e over kt minus 1, which is going to be n times t over t critical to the 3/2. All other particles are in the ground state. Let's call that n naught. So n naught is going to be equal to n minus n star. And I can write that as n times 1 minus t over t critical to the 3/2. Now the n star particles have all the gas's energy. So that energy would be equal to 0 to infinity e rho of e dE over e to the e over kt minus 1. Put in my values. I'm going to get a number that's equal to 3 over, I should say the integral will come out in the form of, we'll write it this way, 0 to infinity x to the n dx divided by e to the x minus 1. It has a value of 3 square root n divided by 4 times 1.341. In other words, the energy would be equal to 0.770 times kt times the number of particles in the excited state, which I can write as 0.770 nkt times t over t critical to the 3/2. So the energy then is actually proportional to t to the 5/2 power.
We have 3 minutes, Dr. Bose.
Thank you. My heat capacity then is going to be equal to dE dt at constant V, and that's going to be 1.9 nk. T over T critical to the 3/2, or 1.9 n star k. So this is not too far from an ideal gas where normally the heat capacity is about 3/2 nk. As the temperature decreases, minus mu over kt becomes smaller, and we get departures from the ideal gas. The attraction between the bosons becomes more and more apparent. CV rises above the ideal value, and we have a plot that looks something like this: CV over nk as plotted against temperature. Here's the critical temperature. We have a sort of a break in the curve. So that's 3/2. This is 1.9. And this is So this is how it looks for Bose-Einstein condensation. This is what we would expect. What we're going to do in the next lecture is to talk about liquid helium. And we're going to investigate liquid helium to see if its behavior, its superfluid behavior, can be considered a Bose-Einstein condensate. Thank you.